Good morning. All right, today we're going to have a look at the effects of negative feedback on amplifiers. All right. That means when we got a op amp and we connect it as an inverting amplifier, a non-inverting amplifier, what will the effects be on my input impedance, my output impedance, and my voltage gain? All right. First of all, we're going to have a look at the non-inverting amplifier. What will the effects be on the non-inverting amplifier? All right. And we're going to look at the input impedance. What's going to happen to my input impedance? We know the device itself got a certain input impedance. All right. Now, when I apply negative feedback, what is going to happen to the overall input impedance of the amplifier? All right. First of all, we can start off by stating that Vin is equal to Vd plus Vf. My input voltage will be equal to that voltage plus my feedback voltage. And we also know the attenuation is equal to Rin divided by Rin plus Rf. But we also know that my feedback voltage is equal to my attenuation times my output voltage. And we substitute that into this equation, then we get Vin is equal to Vd plus the attenuation times Vout. That is equal to Vf. And then they say, remember that my attenuation is equal to Rin divided by Rin plus Rf. Since Vout is approximately equal to the open loop gain times my differential voltage. AOL stands for the open loop gain. That means the gain of the amplifier without any feedback. Then we can say Vin is equal to Vd plus open loop gain times my attenuation times my differential voltage. And then I can take Vd out of the equation. When I take Vd out of the equation, it's equal to 1 plus open loop gain times my attenuation times my differential voltage. And then you can also say that In times Zin is equal to my differential voltage. Ohm's law. Then you can say Vin is equal to 1 plus open loop gain times my attenuation times In times Zin. Now we know if I want to get the overall impedance, it's going to be equal to the input voltage divided by the input current. I repeat, my overall impedance is going to be the input voltage divided by the input current. All right, then we can say Vin divided by In is equal to 1 plus the open loop gain times my attenuation times Zin. But that Zin is the input impedance of the device itself. All right. Then we can say Vin divided by In is the overall input impedance of the closed loop non-inverting amplifier configuration. That's why I can say Zin of a non-inverting amplifier is equal to 1 plus the open loop gain times my attenuation times Zin. I repeat, that Zin again will be of the device itself. And you will find that in the data sheets. All right. That means that will give us an indication that my input impedance will increase by this factor. All right. That means if I had an input impedance, let's say of 1 meg ohm, it will increase by this factor, and that will be quite a large factor. All right. That means I will have a much higher input impedance. All right. Any questions? You must know this proof. The next one is the output impedance. What can we say about the output impedance? Now, as I always mention to this, if I want to calculate output impedance of this thing, what do I need? I need the output voltage and I need the output current. All right. Again, Ohm's law, output voltage divided by output current. That means now we're going to work on the output side. That Zout is of the device itself. All right, now we can say, by applying Kirchhoff's law, we can say the output is equal to the open loop gain times the differential voltage. That will give me that. Minus Zout I out, because I will get a volt drop inside the device. Then they say the differential input voltage VD is equal to Vin minus Vf. Therefore, by assuming that the open loop gain times my differential voltage is much larger than Z out times I out, you can express the output voltage as V out is approximately equal to the open loop gain times V in minus Vf. V in minus Vf will give me my differential voltage. By substituting my attenuation times V out for Vf, because that will give me Vf, then I can say V out is approximately equal to the open loop gain times V in minus my attenuation times V out. Right. Expanding and factorizing the yields, we can say V out is approximately equal to my open loop gain times V in minus the open loop gain times my attenuation times V out. You can take that term across. Then we can say the open loop gain times V in is approximately equal to V out plus the open loop gain times my attenuation times V out. You can take V out as a common factor. Then you'll get 1 plus the open loop gain times my attenuation times V out. All right. Now they say since the output impedance of the non-inverting amplifier configuration, Z out of a non-inverting amplifier is equal to V out divided by I out. That means the output voltage divided by the output current will give me the overall output impedance. And therefore we can say the open loop gain times V in is equal to 1 plus the open loop gain times my attenuation times I out times Z out of a non-inverting amplifier. Now we can go and we divide right through by I out, both sides. Then I get the open loop gain times V in divided by I out is equal to 1 plus the open loop gain times my attenuation times Z out of a non-inverting amplifier. They say the term on the left is the internal output impedance of the op amp, Z out, because without feedback, the open loop gain times V in is equal to V out. Therefore, we can state that Z out is equal to 1 plus the open loop gain times my attenuation times Z out of a non-inverting amplifier. We want this as the unknown. That's why we can say Z out of a non-inverting amplifier is equal to Z out. That is of the device divided by 1 plus the open loop gain times my attenuation. And we know what is the open loop gain. What can I say about the open loop gain? What can I say about the open loop gain? Wake up. Anybody, what can we say about the open loop gain of an op amp? The open loop gain of an op amp is very high. For a 7-for-1, it's 200,000. I repeated how many times? 200,000. That means if you look at this, if you take 200,000, multiply by my attenuation, that's going to be a fairly large amount, all right? That means output impedance will decrease by that factor, all right? Let's go and have a look at this example to illustrate that. Right, example 12.5. They say determine the input and output impedances of an amplifier in figure 12.24. The op-amp data sheet gives Zin. All right, that is now of the device itself. Zin is equal to 2 megohms. Zout is equal to 75 ohms. The open loop gain is equal to 200,000. You see I got a very high open loop or large open loop gain. The attenuation is equal to Rin over Rin plus Rf. That will give me a value of 0,0435. Now, if I go and work out Zin of the, you got a question?
Yes.
Yes.
I was saying that If like the open loop gain is not given, do we assume it's 200,000?
No, you're not going to assume it. They will normally give you the open loop gain, all right? Or they will give you a data sheet, and then from the data sheet, you can determine the open loop gain, all right? You can't assume it, all right? All right, now we're going to work out Z in of a non-inverting amplifier as 1 plus the open loop gain times my attenuation times Z in. This Z in is of the device itself, and when we work it out, we get a value of 17,4 gigaohm. Now you can see it increased from 2 meg to 17,4 gigaohm. That means a much higher input impedance, all right, of the complete circuit. Let's go and have a look at the output impedance. The output impedance is also going to decrease by that factor. And now you can see the output impedance was 75 ohms. Now it decreased to 8,6 milliohms, all right. A much lower resistance or smaller resistance. Now we can also go and work out the gain. Now you can see the gain, the closed loop gain of the non-inverting amplifier is going to be much less in this case than of the device itself. The device itself had an open loop gain of 200,000. With the feedback, my gain is now 23. All right, you can see decreased a lot. All right, but now we're in linear operation and we can use the device. Any questions? Any questions? No questions? Let's go and have a look at the voltage follower. Now, in the case of the voltage follower, what is the voltage gain of a voltage follower? The voltage gain of the voltage follower is 1. Now you can see Z in of a voltage follower is equal to 1 plus the open loop gain because we don't have any attenuation. If I got 1, there's no attenuation, and that will give me the input impedance. That means you will get still a higher input impedance in the case of the voltage follower. The output impedance is also going to decrease a lot because I don't have any attenuation there, because my attenuation is equal to 1. Here's the example of a voltage follower. All right, example 12.6, they say the op-amp in figure 12.5 is used as a voltage follower configuration. Determine the input and output impedances. All right. Now, the same device is used. Now you can see what happens. My input impedance now is going to be equal to 400 gigaohm. There we had an input impedance of what? 17,4 gigaohm. Now it's 400 gigaohm. And if you go and look at your output impedance, it decreased to 375 microamps. All right. Also much smaller than the previous case. All right. Any questions? All right, let's go and have a look at the impedance of an inverting amplifier. The output impedance of the inverting amplifier is going to be exactly the same as the non-inverting amplifier. All right, the output impedance. But my input impedance, now you must remember, I've told you, if my reference is 0 here, the op-amp will always try to make the voltage difference equal to what? 0, all right. That means this point is going to be at virtual ground. Now, if I'm looking into this device, what will my input impedance be? It will be equal to R in, all right. In actual fact, it will be equal to R in plus the impedance of the device in parallel. But now, if I got, for example, a 10 kilo ohm in parallel with the 2 meg, what will the impedance be? It will be 10 kilo ohm. A little bit less than 10, but in actual fact, you can assume it to be R in, all right. All right, if R in is a very high resistance, and they give you the impedance, let's say R in is at 2 meg, and the impedance of the device is also 2 meg. What will my impedance be then? Then it'll be 1 meg, because those two will be in parallel. And here on the next page, they will tell us that. That's why they will tell you there. That's why they will say, if you have a look here, they will show us here virtual ground and they will show us R in. That's why they will say Z in of an inverting amplifier is approximately equal to R in. Why approximately equal to? Because the impedance of the device is in parallel with that. The output impedance, as already mentioned, is exactly the same as for the non-inverting amplifier. Z out of an inverting amplifier, Z out divided by 1 plus the open loop gain times my attenuation. All right. Any questions? No questions. All right. Here's an example on the non-inverting amplifier. On the inverting amplifier. Not the non-inverting, the inverting amplifier. Example 12.7. Find the values of input and output impedances in figure 12.27. Also determine the closed loop voltage gain. The op amp has the following parameters. The open loop gain 50,000. Z in is equal to 4 meg ohms. And Z out is equal to 50 ohms. All right. First of all, Z in we don't have to calculate. Is equal to R in. Is equal to a 1K. The attenuation we can work out because we got R in and we got RF. And that will give me 0,001. The output impedance will decrease by that factor. By this factor, 1 plus open loop gain times my attenuation. And that will give me a value of 980 milliohms. All right. There they say for 0 for all practical purposes, a very, very low value. And a closed loop gain, we're going to look at 100 kilo ohm and 1 kilo ohm. It will give me a gain of 100. All right. Minus sign, I repeat again, minus sign indicates 180 degrees phase shift between my input and my output. All right. Because that's the inverting amplifier, I will have 180 degrees phase shift. Any questions? No questions. All right. All right, the next part of the work, 12.6, bias current and offset voltage. Why do we talk about bias current? What is the input of op amp? What is the input stage of op amp? Anybody? What is the input stage of op amp? It's a differential amplifier. And we got transistors. When we got transistors, we have to bias, all right? Now I'm quickly going to read through here because they're going to tell us basically what I mean by effects of input bias current. They say in figure 12.28, an inverting amplifier with 0 input voltage, ideally the current through R in is 0 because the input voltage is 0, the voltage at the inverting terminal is 0. The small input bias current, I1, is through RF and the output terminal. I1, it creates a volt drop across RF as indicated. Let's quickly go and have a look at the circuit. See what happened here. I got 0 volts in. I should have 0 volts out. But due to that small bias current flowing, it will create a volt drop across RF, all right? And that volt drop across RF will give me a certain output voltage. We don't want an output voltage, but it exists, all right? Now what are we going to do? We must do something to basically rectify that problem, all right? Exactly the same will happen with the voltage follower. All right, these values are normally small values. You see the same. I got a source resistor there, and that will also create a volt drop across here, positive, negative, and I will have a negative output voltage with 0 volts in. That means you don't want an output, but there's going to be an output, a small output. And what are we going to do? We're going to do certain things to basically minimize this effect due to the bias current. We're going to look at the non-inverting amplifier. Exactly the same will happen here in the case of the non-inverting amplifier. 0 volts in, I want 0 volts out, and there should also be 0 volts there, but now what happens? There's a small current flowing, creating a volt drop across RF. We know the op-amp want to make this voltage difference 0, all right? But now due to that current flow, this bias current, it will create a volt drop positive, negative, and I will have output voltage, all right? Unwanted. What do we do to rectify? We do the following to rectify. In the case of the voltage follower, we normally won't have a resistor there, all right? We normally got a wire there, if you remember correctly about the voltage follower. But now we're going to put a resistor there equal to my source resistor, all right? And that will cancel out, and then I will have 0 output voltage if I apply 0 at my input, all right? That's just to do compensation to get rid of that output voltage, all right? That's in the case of the voltage follower. In the case of the other two amplifiers, we can do the following. In the case of the non-inverting amplifier, they call this the compensating resistor. RC stands for the compensating resistor. We take RF and R in, and we get the equivalent parallel resistance, and that will be equal to my compensating resistor, all right? In the case of my inverting amplifier, I will again get the parallel resistance value of R in and RF, and that will be my compensating resistor, all right? Normally we had that connected directly to my reference as indicated there. We didn't have a resistor there, but to compensate for that, we can use that compensating resistor. Because we got a differential amplifier input stage, and we got transistors, and we need bias current. If those things are not identical, there will be a small bias current, and that will cause this problem, or create this problem. All right, we can basically eliminate that by using bi-FET op-amp, and because in the case of FETs, there is no bias current, because the FET is working on a voltage, all right? There's no current there. They say using of a bi-FET op-amp to eliminate the need of bias current compensation. The bi-FET op-amp uses both BJTs and JFETs in its internal circuitry. The JFET is used as an input device to achieve a higher input impedance than is possible with the standard BJT amplifiers. Because of their very high input impedance, bi-FETs is typically have input bias currents that are much smaller than in BJT op-amps, thus reducing or eliminating the need of bias current compensation. All right. We know we're going to compare a FET with a BJT. A FET got a much higher input impedance. All right. Morning. Sorry you're late. You're basically early for the next class, eh? Sit down. First time in the class? Yes, sir. Alright, what we also can do, we look at the following. We use a 741 op amp. That's the op amp you're going to use. We got basically connections here. Offset 0, 0.1 and 0.5. You can see 0.1 and 0.5 on the IC is an offset 0. We can use that. And then we can put a 10 kilo ohm resistor in there, variable resistor, connected to my negative supply as a potentiometer. And by adjusting that, we can also adjust our offset voltage to compensate. All right. That means this IC got the facility to do that, to adjust it to 0 output voltage. That means I got 0 in to get 0 output. That's the facility on the device itself. Any questions? All right. If there is no questions, let's start with the next part of the work. We're going to look at the frequency response of op amp. We're going to look at the open loop frequency response of the op amp. And that is 12.7. 12.7, the open loop response of an op amp. Just for introduction, let's go and have a look at the difference. Let's go and again look at the difference between open loop and closed loop. Open loop, again, there is no feedback. All right. That means the device as it is without any feedback. If I look at closed loop, then I will have negative feedback. Do everybody understand what is the difference between open loop and closed loop? Right, here's the open loop frequency response of op amp. That will be basically the open loop response of a 741. Because if I go and look at the 106 decibels, that will give me equal to, that's the gain. You see here on this axis I got my open loop gain. If I look at 106 dBs, that's going to be equal to, if we're going to look at that per unit, it's going to be equal to 200,000, all right? 0 dBs is equal to what? Per unit. If I look at 0 dBs is equal to what? 0 dBs is equal to what? See here they talk about unity gain frequency. When we cut there. Now 0 dBs is equal to what? It's equal to 1. 0 decibels is equal to 1. That's why we talk about unity gain frequency. All right. Here's my critical frequency. That is a 10 hertz is my critical frequency. Here we call that my mid-range. And from there, I start cutting off at the rate of minus 20 decibels per decade. That's my roll-off. All right. And there I get my unity gain frequency. And that is my critical frequency. I repeat, 0 dB is equal to 1. 106 dBs will be equal to 200,000. And that is the open loop frequency response of an op amp. This one will be basically of a 741. All right. Other op amps, the response will look a little bit different. The critical frequency will maybe differ from this one, but the open loop gain can be higher or it can be lower. All right. Any questions on that? If you read through that part, there they will tell you exactly about what I've told you now. I just want to point out here, there they say the mid-range gain is 200,000, all right. They will also tell us about 0 dBs is equal to 1. Maybe that's... All right, what I want to tell you here about the bandwidth, we normally know the bandwidth. We will look at my upper critical frequency and my lower critical frequency. Electronics 2, chapter 10. But in this case, the op-amp amplify from what? Can the op-amp amplify DC? No. All right, the op-amp can amplify DC. That's why it will start from 0 Hertz up to my upper critical frequency. That's why my bandwidth will be equal to my upper critical frequency. All right, here they give us that unity gain bandwidth. They say, notice in figure 12.36 that the gain steadily decreased to a point where it is equal to unity 1 or 0 dBs. That means 0 dBs is equal to 1. The value of the frequency at which this unity gain occurs is the unity gain frequency designated by FT. It's also called the unity gain bandwidth. All right. But that is when I'm at 1 or 0 dBs. And that was right at the bottom there. Well, you can see there 0 dBs. There's 0 dB, all right? And that is 1, and there's my unity gain frequency, all right? And there is going to be 200,000 or 106 decibels. That means in a data sheet, they can give it to you in decibels, or they can give it to you per unit, all right? All right, I just want to show you this, why we're going to do the next thing. We're going to look at the op-amp or the IC. Inside the IC, you will have the operational amplifier, and the output will be connected to a RC circuit like this. All right, now we're going to have a look what is going to happen in an RC circuit like this. What will that be? A high-pass filter or a low-pass filter? That will be a low-pass filter, all right. That will give me filter action, and that will be a low-pass filter. That's why we're going to look at this RC circuit, all right. Now, when you look at this RC circuit, here's my input, and there's my output. The output is directly across the capacitor, all right. Now, we know if I apply a low frequency, what will my capacitive reactance be? Will it be high or will it be low? My capacitive reactance will be high, all right. That means capacitive reactance is basically the AC resistance of a capacitor, all right. Now, if my frequency increase a lot, what can I say about my capacitive reactance then? It will start decreasing, all right. If your frequency is high enough, it will act like a short circuit. It's not going to be a short circuit, but it will act like a short circuit, all right. That means that resistance will become, AC resistance will become quite low, all right. That brings us to the whole story here. VR over V in, VR is XC, and V in is going to be equal to that plus that, the square root of R squared plus XC squared, all right. Then they say divide both the numerator and denominator to the right of the equal sign by XC, then we'll get VR over V in is equal to 1 upon the square root of 1 plus R squared divided by XC squared. Now the critical frequency, this formula, we're going to use a lot in filters. We're going to use that formula a lot. FC is 1 upon 2 pi RC. Now they say divide both sides by F gives that, then I will get FC divided by F is equal to 1 upon 2 pi RC times F, and that will be equal to 1 upon 2 pi fc times r. All right. They say since xc is 1 upon 2 pi fc, that will cancel out. Then I can say fc divided by f is equal to xc divided by r. My capacitive reactance divided by my resistance. They say substituting this result in the previous equation for V out divided by V in, produce the following expression for the attenuation of the RC lag circuit in terms of frequency. This is a RC lag circuit. Then I can say V out divided by V in is equal to 1 upon square root of 1 plus F squared divided by FC squared. FC is always my critical frequency. All right. F is the frequency and FC is my critical frequency. They say in an op-amp is represented by the voltage gain element with a gain of the open loop mid-range plus a single RC lag circuit is shown in figure 12.38. It is known as a compensated op-amp. The total open loop gain of the op-amp is produced by the mid-range open loop gain and the attenuation of the RC circuit. That means in op-amps we get sometimes much more than one stage like that, but we'll come to that a little bit later. Here we're only going to look at one stage. You see, here's the op-amp, one stage with my RC lag circuit, and then I can say my open loop gain is equal to the open loop mid-range value divided by the square root of 1 plus F squared divided by Fc squared. All right, and here they're going to give us an example, example 12.8, to illustrate that for different frequencies. They say determine the open loop gain of the following values of F. Assume that FC open loop is equal to 100 Hertz and the open loop mid-range is equal to 100,000. All right. Now we're going to start off by using a frequency of 0. Now if I got a frequency of 0, then my open loop gain is going to be equal to 100,000. All right. Then I'm going to have 10 Hertz, the frequency increase. Then I will have 99,503. Then I increase to 100 Hertz. Then it's going to be 70,710. And then I'm going to increase to 1,000 Hertz. Then it's going to be 9,950. You can see as the frequency increase, what happened to the open loop gain? What happened to the open loop gain? It decreases. The higher the frequency, the lower the open loop gain. Just to show you why. As my frequency increases, what happened to the open loop gain? It decreases. You see, if you're there at 10 kilohertz, I will have around about 50 dBs. All right. The higher the frequency, the lower the gain. All right. Because I got that roll off of minus 20 dBs per decade. That means higher frequency, lower the gain. You with me? And that's basically what I illustrate here in that example. Then there's also, yes.
Normally, this one, you say that the higher the frequency, the lower the gain.
Yes.
But this one got higher gain.
What is the higher? No, that is 70,710. Not 70 comma that. that is 9,950. There you had 100,000. You with me? That is not 100, 00. That is 100,000. That is 99,503. That is 70,710. And that is 9,950. You with me? All right. All right. When we look at the RC lag circuit, there's also going to be a phase shift. All right. And here's the formulas for the phase shift. Theta is equal to minus arctan R divided by XC, or we can calculate theta is equal to minus arctan divided by F divided by FC. All right. That is to determine the phase shift that exists at certain frequencies. Right, that's what's going to happen. We look at this. If I apply a sine wave to this RC lag circuit, what happens? You will notice the output will lag the input by that amount of degrees. All right. But that will be determined by the frequency. All right. They say the negative sign indicates the output lags the input. This equation shows that the phase shift increases with frequency and approaches minus 90 as F become much greater than FC. That means if your frequency becomes much larger than your critical frequency, I will move in the direction of 90 degrees. All right. Minus indicates it lags. All right. To illustrate this, example 12.9, calculate the phase shift for the RC lag circuit for each of the following frequencies and then plot the curve of phase shift versus frequency. Assume FC is equal to 100 Hz. My critical frequency is 100 Hz, and I got 1 Hz, 10 Hz, 100 Hz, 1,000, and 10,000. All right. Now we're going to look at 1 Hz. I will get a value of minus 0,573 degrees. 10 Hz is going to be minus 5.71. 100 Hz will give me minus 45 degrees. 1,000 Hz will give me minus 84.3 degrees. And then when I go to 10,000 Hz, it will go to 89.4 degrees. All right. That means it approaches 90 degrees. And then I plot that frequency against phase shift. And now there you can see if I plot that frequency against phase shift. At low frequencies, I got a low, very small phase shift. And as the frequency increases, my phase shift also increases. All right. Approaching minus 90 for that one stage. All right. Next lesson, that will be on Thursday. Thursday, we'll look at the overall frequency response of the op-amp. All right, we will look at the overall frequency response of the op-amp, and there you'll find we will use more than one stage. That will be for our next lesson on Thursday. The overall frequency response. In an op-amp package inside the device, we can sometimes find more than one op-amp with three lag circuits, all right? And if we consider op-amp 1, we got that frequency response with a roll-off of minus 20 dBs per decade, and we will have our critical frequency FC. For the second op-amp, AV2, we will have also the open loop gain, and we will have our roll-off and our critical frequency FC2. For the third op-amp, AV3, we will also have our open loop gain and our roll-off and our critical frequency FC3. That is the individual responses of the device. In the next one, in the composite response, because our gains is in decibels, the overall gain will be the sum of all three gains because it's in dBs. If it wasn't in dBs, we must multiply. Because in dBs, we can just add to get a total gain. And then we got the different roll-offs for the first one, the second one, and the third one with our three critical frequencies. Our overall phase shift, theta total, is equal to minus arctan F divided by FC1. For the second stage, it's going to be minus arctan F divided by FC2 and minus arctan F divided by FC3. That will give me my total phase shift, my overall phase shift. To illustrate this, we can have a look at example 12.10. They say a certain op-amp has three internal amplifier stages with the following gains and critical frequencies. Stage 1 is AV1 is equal to 40 dBs. The critical frequency 1 is equal to 2 kilohertz. Stage 2, AV2 is equal to 32 dBs and FC2 is equal to 40 kilohertz. And stage 3, AV3 is equal to 20 dBs and FC3 is equal to 150 kilohertz. They say determine the open loop mid-range gain in dBs and the total phase lag when F is equal to FC1. The open loop mid-range gain is going to be AV1 plus AV2 plus AV3, and that will give me a total of 92 decibels. The total phase shift is going to be minus arctan of 1, minus arctan of 2 divided by 40, and minus arctan 2 divided by 150, and that will give me a total phase shift of minus 48,6 degrees. Thank you.